Tonight, we begin with two tiny points of light. Not the bright kind, not the kind you notice on a clear night when you step outside and look up. These were the faint, almost invisible kind. Two small red pinpricks sitting about 12.8 arcseconds apart in a single processed image, glowing only in the deepest infrared wavelengths the James Webb Space Telescope is capable of seeing. And when the team that found them ran them through every standard test astronomers have relied on for 3 decades to identify distant galaxies, those two tiny lights came back as the farthest objects ever recorded in the history of observational astronomy. Not the farthest by a small margin, the farthest by an enormous one. Light that, if the interpretation was correct, had been traveling toward us since the universe was perhaps 100 million years old. Earlier than any galaxy had any right to exist. Earlier than the first stars were expected to have ignited. The team did not publish. They waited. They took the same image again, a full year later, and they watched both of those tiny red points move sideways across the sky. Galaxies at the edge of the observable universe do not move. Whatever these two things were, they were not galaxies. So settle in. Find your comfortable position. If you haven't already subscribed, there's a button down below, and it costs you nothing. What those two red dots actually turned out to be is sitting far closer to Earth than the Pleiades, the little cluster of stars you can see with your naked eye on a winter night. And the answer is going to quietly reshape the way you think about the edge of our galaxy and everything beyond it. In the early hours of January 20th, 2025, a sequence of commands was transmitted from a control room on Earth to a spacecraft drifting in deep space at a distance of about 1.5 million kilometers from our planet. The spacecraft was the James Webb Space Telescope, and on that particular night, it had been asked to turn its 18 hexagonal mirror segments, each one aligned with extraordinary precision, toward a small and seemingly unremarkable patch of sky in the southern constellation of Carina. The patch of sky itself was, of course, anything but unremarkable. What lay in that direction was the most famous galaxy cluster in modern cosmology, an object that has served for nearly 2 decades as some of the clearest evidence we have that dark matter exists. Astronomers call it the bullet cluster. In 2006, a research team led by Douglas Clow used a combination of gravitational lensing data and X-ray imaging to demonstrate something quietly profound. When two massive galaxy clusters had collided and passed through each other long ago, the ordinary gas in each cluster had slowed down and piled up in the middle, the way two streams of water might splash together. The galaxies themselves, held together by something other than gas, had kept moving and passed right through. The mass of the combined system, as measured by how much the background light was bending around it, was not in the same place as the gas. The mass was offset from the gas in a way that simply cannot be accounted for without invoking some additional invisible substance holding the galaxies together, while the visible matter lagged behind. The light was bending in a way the gas alone could not explain. The mass was somewhere the X-rays could not find it. The conclusion has never been seriously challenged. The universe is largely composed of something we cannot see directly. If someone asked you to point to the single most convincing image supporting the existence of dark matter, the bullet cluster is the picture you would show them. What is less widely known about the bullet cluster, but important for the story we are about to explore, is that it also happens to be one of the most useful natural telescopes in the sky. The sheer concentration of mass in the cluster bends and magnifies the light of everything sitting behind it, stretching distant galaxies into thin arcs and brightening faint objects that would otherwise fall far below detection. For astronomers who want to study the earliest galaxies in the universe, the ones that formed within the first few 100 million years after the Big Bang, the bullet cluster region is a natural first choice. The cluster does some of the work of a magnifying glass for free. The observing program running on the James Webb that January night had a name and a program number. It was JWST General Observer Program 4598 with the title Silver Bullet for Dark Matter. The principal investigators were Marusha Brodach at the University of Ljubljana, Alexei Refich, also at Ljubljana, and Martin Sikic at St. Mary's University in Halifax. The program was designed to use the bullet cluster's gravitational lens to image the field at great depth using 8 different infrared wavelength filters. Those filters ranged from a short wavelength band centered near 0.9 microns, designated F090W, through filters at 1.15, 1.5, 2.0, 2.77, 3.56, and 4.10 microns, and finally a long wavelength filter at 4.44 microns called F444W. Each filter captured a slightly different slice of the infrared sky. Each was exposed for around 6,400 seconds, just under 2 hours. By the time the night's observations were complete and the telescope had returned to its default orientation, the deepest infrared image ever obtained of the bullet cluster region was sitting in the spacecraft's data buffer, waiting to be transmitted back to Earth. When the processed images arrived at the science teams a few days later, almost everyone scanning the new data was looking for the same category of object. The gravitational magnification of the bullet cluster was expected to reveal galaxies sitting far behind it in cosmic time, objects whose light had been traveling toward us for more than 13 billion years, stretched by cosmic expansion into the longest infrared wavelengths the James Webb can detect. The anticipation was that the longest wavelength filters, the ones farthest into the infrared, would be where the oldest galaxies finally appeared. Much of the field looked exactly as expected. There were dozens of background galaxies, some bright and some faint, visible across a range of filters. There were foreground stars belonging to our own Milky Way, easily recognizable because they showed up clearly in every filter from blue to red. There were the usual technical details to attend to: hot pixels to mask, instrumental artifacts to clean up, calibration to finalize. And then, in one region of the field, 12.8 arcseconds apart from one another, there were 2 small, faint red points of light that did not look like anything else in the image. To give you a sense of what 12.8 arcseconds means in practice, it is roughly the angular width of a single human hair held at arm's length. The 2 dots were separated by that tiny amount, close enough to suggest they might be physically related to each other, or might simply be an unrelated coincidence of position. Both were extremely faint, and both were completely invisible in the shorter wavelength filters, in F090W, F115W, F150W, and F20W. They simply did not appear. They were absent in the next filter as well, F277W, with one possible exception. The object later catalogued as bullet BD2 showed the faintest possible trace of brightness at that wavelength and grew progressively brighter toward the longer filters. The other object, catalogued as bullet BD1, did not appear at all until F356W, and then brightened sharply in the final F444W filter. In the language of observational astronomy, objects with this behavior are called dropouts. They have dropped completely out of the shorter wavelength images and are present only in the reddest, longest wavelength data. And when a dropout behaves the way these 2 were behaving, it means something very specific, or at least it usually does, about how far away the object is. This is the moment in the story where the team permitted themselves a particular kind of quiet hope. The 2 faint red points in the bullet cluster field had every visual characteristic of extremely distant galaxies. They had the dropout signature. They were in the magnified zone of one of the most powerful natural lenses in the sky. They were faint in exactly the way you would expect the most remote galaxies ever observed to be faint. And their overall color distribution, judging by the pattern of brightness across filters, was consistent with starlight that had been stretched by the expansion of the universe for so long that it had been pulled entirely out of visible wavelengths and now appeared only in the deepest infrared. If interpreted as distant galaxies, the object that dropped out at F356W, bullet BD1, would correspond to something at a redshift of around 30. The object that dropped out at F277W, bullet BD2, would correspond to a redshift of around 20. To understand how extreme those numbers are, the current spectroscopically confirmed record for the most distant galaxy ever observed is held by an object called JWST Z14-0, seen as it was approximately 290 million years after the Big Bang, at a redshift of 14.32. A redshift of 30 would place an object as it appeared when the universe was about 100 million years old. A redshift of 20 would correspond to around 180 million years after the Big Bang. Both figures fall well inside the window when standard models of galaxy formation suggest that assembled luminous structures simply should not yet exist. The team had something potentially extraordinary on their hands, and they knew it. They also knew the field's recent history. The James Webb had been taking science data for about 2.5 years at that point, and the community had already gone through at least one cycle of dramatic candidate discoveries at extreme redshifts that were subsequently revised, reclassified, partially confirmed, and in some cases still actively debated. The entire discipline was in a complicated state. The standard cosmological model, lambda cold dark matter or lambda CDM, was simultaneously producing predictions that sometimes matched the data comfortably and sometimes appeared to be under genuine strain. Into that already complicated landscape, the Brodich team now had two new faint red points that would, if taken at face value, represent some of the most distant objects ever found in any image of any sky. They knew the standard of evidence required. Extraordinary findings require extraordinary verification, and they were nowhere near ready to make any public claim at all. What they decided to do over the following 12 months, and through a second visit to the bullet cluster field, would turn out to be the most careful and patient piece of work in the entire story. But before we get there, before we arrive at the spectroscopy, the second observing campaign, the proper motion measurement, and the slow, quiet realization that something remarkable had been hiding in those images all along, we need to step back and understand the method itself. We need to understand why the dropout technique became the dominant tool of high redshift galaxy discovery 30 years ago, and what the underlying assumption is that connects an object invisible at short wavelengths but bright at long wavelengths to an object at the very edge of the observable universe. Because the strange thing that is about to happen in this story, the thing no one was quite expecting, is not that the method was wrong. The method was right. These two faint red points were genuine dropouts. They genuinely had the spectral signature that distant galaxies carry. The difficulty was that something else entirely, something no one looking at those images had been thinking about, also produces that same spectral signature in the same wavelength range and is essentially indistinguishable from a distant galaxy in every measurement except the one the team was about to spend a year collecting. In 1996, a paper appeared in the Astrophysical Journal that has since accumulated more than 3,000 citations and quietly transformed what was possible in observational cosmology. The lead author was Charles Steidl, working with 4 colleagues, Mario Giovalisco, Max Patini, Mark Dickinson, and Kurt Edelberger, and the idea they introduced was elegant in its simplicity. Take an image of a patch of sky through several different filters spanning from the ultraviolet into the visible range. Look for objects that are bright in some of those filters and absent in others. More specifically, look for objects that vanish entirely below a certain wavelength but show up cleanly above it. That sharp transition, that sudden drop in brightness, is the signature of a distant galaxy. The physical reason it works comes down to hydrogen. The early universe was made almost entirely of hydrogen and helium. More than 13 billion years later, hydrogen is still the dominant element, distributed not only in stars and galaxies, but spread thinly through the vast spaces between them. And those hydrogen atoms do something very specific to the light that travels through them from distant sources. They absorb any photon whose wavelength is shorter than what astronomers call the Lyman limit, a wavelength of about 912 angstroms, which corresponds to the precise amount of energy needed to strip the single electron away from a hydrogen atom and ionize it. Photons with wavelengths shorter than that threshold are absorbed. Photons with wavelengths longer than it pass through relatively unimpeded. The practical consequence for any galaxy observed from a great distance is a sharp cliff in its spectrum. Above the Lyman limit, the galaxy's light arrives mostly intact. Below it, the light has been largely absorbed by intervening hydrogen. There is a step, a place where the brightness drops suddenly and steeply. For a nearby galaxy, that step falls deep in the ultraviolet, where ground-based telescopes cannot easily observe anyway. But the universe is expanding, and that expansion stretches the wavelengths of all the light traveling through it. The more distant a galaxy, the longer its light has been traveling, and the more that wavelength has been stretched. At a redshift of 3, the Lyman break, which begins at 912 angstroms when the light leaves the galaxy, arrives stretched to around 3,650 angstroms, near the blue end of the visible spectrum. At redshift 7, it shifts to around 7,300 angstroms, into the red end of the visible. At redshift 14, it stretches into the near-infrared, at about 14,000 angstroms. At redshift 20, it sits near 19,000 angstroms. At redshift 30, it reaches around 28,000 angstroms, well into the infrared range that only a telescope like the James Webb can reach. At each of those redshifts, the pattern is the same. There is a wavelength below which the galaxy is dark, and above which it glows. If you observe a patch of sky through a series of filters that bracket the expected location of the break for a given redshift, you can search for objects that are absent in the filters below the break and present in the filters above it. That object is, in the vast majority of cases, a galaxy sitting at roughly the redshift you were looking for. Steidl's original paper applied the technique to galaxies at redshift around 3, where the break falls in the near ultraviolet. Those galaxies became known as Lyman break galaxies, and the technique became the primary method of high redshift galaxy discovery for the following decade. The Hubble Deep Field, obtained in 1995, was filled with dropout candidates that the Lyman break technique helped characterize. The Hubble Ultra Deep Field, taken in 2004, pushed the technique to redshifts of 6 and above. The Candles survey, conducted with Hubble between 2010 and 2013, grew the dropout catalog into the hundreds of confirmed sources. By the time the James Webb launched in December 2021 and began taking science data in mid-2022, the dropout technique had been thoroughly validated across thousands of galaxies, spanning a range of redshifts that Steidl's generation could barely have imagined. The James Webb extended the reach of the technique in the most dramatic way yet. Because the telescope operates almost entirely in the infrared, with detectors sensitive from roughly 0.6 to 28 microns, it can detect the Lyman break for galaxies at redshifts no previous instrument could touch. The near-infrared camera on board, called NIRCam, carries a suite of broadband filters that astronomers recognized immediately as ideal for dropout work. F090W catches galaxies dropping out at around redshift 7. F115W finds dropouts near redshift 8 or 9. F150W reaches to around redshift 11. F200W to around 14. F277W to around 20.
F356W to around 25 to 30. F444W is the final broadband filter, the one where a dropout could mean a galaxy at the very outermost boundary of the observable universe.
When the Bullet Cluster team looked at their first epic images and saw two faint red points appearing only in the longest filters, they were seeing precisely the class of object the dropout technique had been developed to find. The signal was clean. The spectral cliff was sharp. The colors matched what the method predicted. By 30 years of accumulated validation on thousands of previous galaxies, those two faint red points had every right to be considered candidates for the most distant objects humanity had ever detected. What the team also carried in mind, however, was that the dropout technique has a documented failure mode. It had been described in the research literature for at least a decade. The Lyman break is not the only sharp spectral transition that can make a faint infrared object look like a dropout. There is another category of object, one much closer to home and produced by entirely different physics, that leaves an almost identical pattern in broadband photometry at nearly the same wavelengths. That category is a class of extremely cool failed stars called Y-class brown dwarfs, and as the James Webb surveys had pushed to greater depths and more extreme redshifts, the contamination from these objects had been appearing with increasing frequency. Heinlein and colleagues had published a series of papers in 2024 and 2025 identifying brown dwarfs masquerading as high redshift galaxy candidates in the Jades and Sears deep fields. Langerudi and Hjorth had published a paper in 2023 identifying 3 brown dwarfs that had been confused with what the field was calling little red dots, compact, red, active galactic nuclei candidates. The contamination was a recognized problem. What nobody yet knew was how serious it truly was, or whether the most extreme high redshift candidates ever found fell on the contaminated side of the catalog or the genuine side. This was the landscape the Bullet Cluster team now inhabited. 2 perfect dropouts in a gravitationally magnified field. They could have published. They could have submitted a paper announcing the discovery of galaxies at redshifts 30 and 20 and let the community begin the process of verification. They did not. Instead, they applied for spectroscopy with the James Webb's near-infrared spectrograph. And then they did something that is genuinely rare in the fast-moving world of modern astronomy. They waited.
To understand what was at stake when the Bradich team looked at those processed first epic images, you need to understand what it would have meant if Bullet BD1 and Bullet BD2 were what they appeared to be. You need to understand the timeline of the universe. The universe is approximately 13.787 billion years old. This figure comes from the Planck satellite's 2018 Cosmological Parameters paper and has remained stable across multiple independent lines of measurement. The Big Bang marks the beginning of time in this picture, the moment of infinite density and temperature from which everything expanded outward. The first 380,000 years were a period of hot, dense plasma, so opaque that light could not travel any meaningful distance before being scattered by the sea of free protons and electrons surrounding it.
At around 380,000 years after the Big Bang, the universe had cooled just enough for protons and electrons to combine into neutral hydrogen atoms. With no more free charges to scatter them, photons were finally able to travel freely through space, and the universe became transparent for the first time. The faint afterglow of that moment is what we observe today as the cosmic microwave background, cooled by cosmic expansion from an original temperature of about 3,000 Kelvin down to its current 2.725 Kelvin. After that first flash of freedom, the universe entered a second dark period. Neutral hydrogen filled space, but no significant structures had yet formed, no stars had yet ignited, and the cosmos was dark and quiet. The first stars are believed to have lit up somewhere between 100 million and 200 million years after the Big Bang. These early stars, what astronomers call population 3 stars, are thought to have been enormous, brilliant, and short-lived, made entirely of hydrogen and helium,
since no heavier elements had yet been forged. The first galaxies, assembled from clusters of these early stars, are thought to have formed somewhere between 300 million and 500 million years after the Big Bang.
The spectroscopically confirmed record for the most distant galaxy ever observed belongs to an object called JWST-Z14-0, observed by the James Webb and reported in 2024 by Stefano Carniani and his collaborators at a redshift of 14.32. That galaxy is being seen as it was when the universe was about 290 million years old. Just behind it sits a candidate called MALM-Z14, reported by Rohan Naidu and collaborators in 2026 at a comparable redshift. These confirmed and near-confirmed galaxies are already, by the standards of pre-JWST models of galaxy formation, somewhat puzzling, brighter and more abundant than expectations suggested. The field has been working to understand whether this works unusually efficient early star formation, unusually clean stellar populations, or some other physical effect. A 2025 paper by Aaron Young, Rachel Somerville, and Changa argued that the lambda CDM cosmological model is not actually broken by these observations, and that the apparent abundance of bright early galaxies can be accommodated within the uncertainties of the model if one is careful. But the margin is narrow. The community is watching.
Now, consider what the two bullet cluster dropouts would have meant if accepted as genuine galaxies. Bullet BD2, the object that dropped out of F277W, would correspond to a galaxy at around redshift 20. The universe at that moment was about 180 million years old. That is more than 100 million years earlier than the current confirmed record. It is in a part of the cosmological calendar where galaxy formation models, even when pushed to their outer limits, have no comfortable mechanism for producing a galaxy bright enough to be detected, even with the magnifying assistance of a foreground cluster.
Bullet BD1, the object that dropped out of F356W, is even further out. At a redshift of roughly 30, the universe was around 100 million years old. At that point in cosmic history, individual luminous objects, the very first stars, might have only just been igniting. There should not yet be a galaxy. There should be, at most, small, isolated pockets of brilliance scattered across an otherwise dark and hydrogen-filled sky. Anything bright enough to be detected, even with the best magnification the James Webb and the Bullet Cluster together can provide, would be something entirely outside the comfort zone of every current model of structure formation. If the team had been able to confirm both objects as genuine high-redshift galaxies, the paper would have been one of the most consequential in modern cosmology. It would have, in plain and unavoidable language, broken the standard model of early galaxy formation. Every framework describing how galaxies assembled in the first moments of cosmic time would have needed to be reconsidered. The lambda CDM model would have been forced to accommodate either far more efficient early star formation than any simulation suggests, or some entirely new physics, or some unanticipated mechanism for producing luminous structures in the universe's first 100 million years. The implications were enormous. The headlines would have written themselves. The Brodich team understood this, and they understood, precisely because the implications were so large, that they had to be careful. The history of cosmology is rich with dramatic-looking results that turned out to have quieter explanations. The 2014 reports by the BICEP2 collaboration of a gravitational wave signal from inflation, for example, later turned out to be dominated by contamination from dust in the foreground Milky Way, once Planck satellite data was used to subtract the dust contribution. Several instances of apparent excesses in dark matter direct detection experiments have resolved into calibration issues. The community has been here before. Anyone who has spent more than a few years in the field develops an intuition for the kind of result that demands extraordinary patience before extraordinary publication.
The Bullet Cluster team had that intuition, and they had a specific, named concern sitting in the back of their minds. By early 2025, The field had already developed an uncomfortable awareness that extremely cold brown dwarfs in our own galaxy could produce broadband color patterns that closely mimicked those of high redshift galaxy candidates in James Webb imaging. Heinlein and colleagues had published their first JADES brown dwarf candidate paper in 2024, identifying objects in the deepest extragalactic James Webb surveys that turned out, on follow-up examination, to be cold local stars rather than distant galaxies. Langarudi and Hjorth had identified 3 brown dwarfs in 2023 that had been confused with little red dot AGN candidates. Burgesser and collaborators had announced 7 cold brown dwarfs from the JWST Rubies program. And then there was Capitaro.
Capitaro was a nickname the field had settled on for a particular dropout candidate found by Mara Gandolfi and collaborators in the Cosmic Evolution Early Release Science Survey, a JWST program that had imaged a small area of sky in the constellation Bootes. The object's formal designation in the survey catalog is CEERS U10058. The nickname came from an obscure peak in the Apennines, chosen with a quiet appreciation for small, striking things that a team keeps returning to. Capitaro had a photometric redshift estimate of approximately 32. The universe at that redshift would have been about 90 million years old. If real, Capitaro would have been, by an enormous margin, the most extreme high redshift galaxy candidate ever found, twice as far back in time as the spectroscopically confirmed record holder, sitting in a part of the cosmological calendar where galaxies should have had no time yet to form. The discovery paper, archive preprint 2502-02637, had been published in February 2025. The team had been openly cautious about their own interpretation, explicitly raising the brown dwarf possibility as an alternative. The community had been waiting for follow-up data. The Bullet Cluster team knew about Capitaro. They knew about the Heinlein contamination work. They knew that the deeper the James Webb surveyed and the more extreme the candidates that emerged, the more critical it was to verify any extreme high redshift object through multiple independent tests before committing to any interpretation. So when Bullet BD1 and Bullet BD2 appeared in the first epic images that January, they did not write a discovery paper. They did something different. They applied for spectroscopic time on the James Webb's near-infrared spectrograph, and they began planning a second observing campaign. What they planned to test for in that second campaign was something a galaxy at the true edge of the observable universe absolutely must not do. They were going to look for sideways motion, proper motion, the slow drift of a nearby object across the sky over time. If they found it, everything about the interpretation of those 2 faint red points would change in a single measurement, from the most distant galaxies ever seen to objects right here inside our own galaxy, drifting slowly through the disk of the Milky Way, wearing a disguise. They did not yet know what they would find. They had a year to wait. To really understand why the Bullet team chose patience over publication, we need to spend some time with Capitaro. We need to understand what had already happened to the field's previous most extreme galaxy candidate, and why the lessons of that case were sitting quietly in the back of every careful astronomer's mind by the time Bullet BD1 and Bullet BD2 appeared. The CEERS survey that produced the Capitaro discovery was one of the earliest large James Webb programs to image a deep extragalactic field. The acronym stands for Cosmic Evolution Early Release Science. The program was led by Stephen Finkelstein at the University of Texas at Austin and took data in the Bootes field throughout the second half of 2022 and into 2023. The field is a small one, only about 100 square arc minutes, but it was imaged in 9 different NIR-CAM filters and partially observed with NIR-SPEC spectroscopy as well. For many early high redshift surveys, the CEERS catalog became one of the first places to test the dropout method at the most extreme depths the James Webb could reach. Buried inside that catalog, at the celestial coordinates of right ascension 14 hours, 14 minutes, 32.97 seconds, and declination plus 52 degrees, 47 minutes, 52.11 inch, sat a faint red point of light that Mara Gandolfi, Julia Rodigiro,
Marco Castellano, Adriano Fontana, and colleagues had found during a systematic search of the survey's longest wavelength filters. They gave it the catalog number U10058 in the CEERS internal naming system.
The object had an apparent magnitude in the F444W filter of about 27.68, faint but detectable. It was undetected in every filter below 3.5 microns, and between the F356W filter and the F444W filter, the brightness jumped by more than 3 magnitudes, a factor of more than 15 in actual light intensity across less than 1 octave of wavelength. It was the sharpest dropout signature in the entire Sears catalog. If red is a galaxy, U10058 had a photometric redshift estimate centered near 32, with broad error bars, as is always the case with photometric estimates derived from a small number of filter detections, but with a central value that commanded attention. The age of the universe at redshift 32, using the Planck cosmological parameters, works out to approximately 90 million years after the Big Bang. That is 200 million years earlier than the current spectroscopically confirmed record holder. It sits in the era when, according to galaxy formation models, calibrated against the entire previous body of observational data, individual stars might just barely be starting to exist. But galaxies bright enough to be detected across that distance simply should not. Gandolfi and her collaborators faced a choice similar to the one the Bullet team would encounter 2 years later. They could have framed the paper as a record-breaking galaxy discovery. Instead, they did something more careful. They wrote the paper to explicitly acknowledge 3 separate possibilities: a genuinely record-breaking high redshift galaxy, a dust-obscured galaxy at a much lower, more comfortable redshift, or an ultra-cool brown dwarf in the Milky Way disk. The archive preprint, posted on February 4, 2025, was titled deliberately to reflect that uncertainty: Ultra-High Redshift, or Closer-by Dust-Obscured Galaxies, Deciphering the Nature of Faint, Previously Missed F200W Dropouts in Kears. They presented the data. They acknowledged the ambiguity. They called for follow-up observations. The follow-up arrived over the following year. The team obtained additional imaging from CEERS and neighboring James Webb programs. They refined the photometry. They consulted with brown dwarf specialists on the available spectral templates for Y-class brown dwarfs. They worked with Andrea Ferrara on an exotic alternative hypothesis that U10058 could be a pair instability supernova, the catastrophic explosion of a very massive primordial star at moderate redshift, visible as a transient point of light. They collaborated with Kevin Hainline's group on the systematic contamination question. By the time the definitive analysis appeared in Astronomy and Astrophysics in early 2026, as paper A&A 706-A364, the title had become simpler and more direct: Mysteries of Kapataro, investigating the puzzling nature of an extreme F356W dropout. The nickname had taken firm hold by then. The paper laid out the case for each of the 3 interpretations with careful precision. The galaxy interpretation was not impossible. The photometric fit at redshift 32 was technically consistent with the data, and lensing magnification from a nearby foreground galaxy could account for some of the apparent brightness. Against it, a redshift of 32 would place the object outside the comfort zone of every galaxy formation model, with required absolute ultraviolet magnitude of -21.5, corresponding to a stellar mass that should not yet exist at that epoch. The case for the brown dwarf interpretation rested on the fact that Y-class brown dwarf atmospheric templates, specifically the Sonora Chihuahua and Atmo 2020 model grids, produced excellent fits to the photometry. The best fits suggested a Y2 or Y3 brown dwarf with a surface temperature somewhere between 300 and 400 Kelvin, sitting at a distance ranging from about 127 to 1800 parsecs from Earth. The statistical probability of detecting a Y2 brown dwarf in the CERS survey volume was approximately 2.2%. For a Y3, about 0.9%. Small, but not absurd, especially given how many total candidates the survey had produced and how systematically the contamination issue had been appearing across deep JWST fields. The pair instability supernova interpretation, developed by Ferrara and independently by a team led by Mangin and John, proposed that a primordial star of approximately 140 to 260 solar masses would end its short life in a particular kind of explosion, in which the unstable production of electron-positron pairs in the star's hot core leads to a sudden loss of pressure support, triggering a runaway thermonuclear reaction that tears the star entirely apart, leaving no remnant. The resulting light curve has a characteristically slowly declining shape that, when placed at high redshift, would be stretched by cosmological time dilation from weeks into years, and whose spectral peak would shift into the long wavelength filters where U-1058 was actually observed. The Gandolfi A&A paper did not declare a winner. It laid out the evidence, noted that the photometric fit at redshift 32 was the weakest of the three options by chi-squared, and that the brown dwarf and pair instability supernova fits were broadly comparable. The crucial constraint the team could offer was an upper limit on proper motion, assembled from a 2.3-year imaging baseline combining several James Webb observations of the field. That upper limit was approximately 0.137 arcseconds per year. At a distance of 100 parsecs, a brown dwarf would typically be moving at 50 to 100 milliarcseconds per year. At 1,000 parsecs, the same brown dwarf would move at 5 to 10 milliarcseconds per year. The CEERS upper limit was consistent with a brown dwarf anywhere from about 100 to 1,800 parsecs away. It was also, of course, consistent with a completely stationary extragalactic source at any distance. The measurement on its own was inconclusive. What the community needed was a precision proper motion detection, or a clean non-detection, at far higher accuracy. Kappa Taro was the case study sitting in everyone's mind when Bullet BD1 and Bullet BD2 appeared in the Bullet cluster imagery in January 2025. The Bullet team knew exactly what they were looking at. Two new dropouts in a different field. Similar broadband colors. The same fundamental ambiguity. The most distant thing in the image might also be the closest thing in the image. That phrase began circulating quietly in the team's internal discussions. Half metaphor, half active suspicion. They applied for James Webb near-spec time. They got it. The follow-up spectroscopy was scheduled for March 27, 2025, about 2 months after the first epoch of imaging. And for the more decisive proper motion test, they applied for a second epoch of near-cam imaging through a separate James Webb program led by Seiji Fujimoto and Dan Ko, the Venus program, JWST GO 6882. The second epoch was scheduled for January 21, 2026, 1 year and 1 day after the first. The baseline they would achieve would be exactly 1.03 years. That precision, if everything went as planned, would let them measure the positions of Bullet BD1 and Bullet BD2 to within a few milliarcseconds per year, enough to settle the question decisively and permanently. So they waited. The near-spec spectroscopy of Bullet BD1 and Bullet BD2 was obtained on the night of March 27, 2025, using the PRISM mode of the instrument's micro-shutter array. PRISM mode is the instrument's low-resolution spectroscopic configuration, delivering coverage of the full near-spec wavelength range, from about 0.6 to 5.3 microns in a single exposure. The resolving power in this mode is modest, around 100 at most wavelengths, which means the spectra would not show fine atomic or molecular features in detail, but they would reveal the overall shape of each object's spectrum, the approximate location of any spectral breaks, and the broad absorption features that distinguish different kinds of astrophysical objects from one another. For two faint dropouts, whose fundamental need was simply to determine whether their spectral energy distribution was more consistent with a galaxy at redshift 20 or 30, or with a brown dwarf at a few hundred Kelvin, or with something else entirely, the PRISM was exactly the right tool. The spectra came back within a few weeks. The reductions were clean, the calibration standard, the data quality solid. When the team examined them, the picture was complicated. The signal was clear. The shape of each spectrum was visible across exactly the wavelength range where any high redshift galaxy break or any cool brown dwarf's methane absorption features would appear. The fits, when applied to both candidates, told a story that was genuinely ambiguous. Both the brown dwarf interpretation and the high redshift galaxy interpretation were consistent with the data. The brown dwarf fits had slightly better chi-squared values,
but the galaxy fits were not ruled out. By the end of spring 2025, the near-spec spectra had shifted the team's internal confidence away from the galaxy interpretation and toward the brown dwarf interpretation, but not decisively enough to publish. They needed the proper motion test, so they waited.
Summer came and went. The team worked on other projects. They watched Heinlein's group identify more brown dwarfs in the JADES and CE's catalogs. They read a case study of an object designated JADES GS-BD9, a T5 to T6 brown dwarf at a distance of roughly 2 kiloparsecs, with a measured proper motion of 20 plus or minus 4 milliarcseconds per year, published as an archive preprint in mid-July 2025. That result was important for the Bullet team because it demonstrated that the James Webb could measure proper motions at the milliarcsecond level over multi-year baselines, that the slow drift of nearby brown dwarfs across the sky was detectable, and that a combined spectroscopic and astrometric measurement could conclusively identify a contaminant. Autumn arrived. The CEERS team published their definitive Capitaro analysis paper in Astronomy and Astrophysics. The photometric fit favored the brown dwarf interpretation over the galaxy and pair instability interpretations, but with overlapping uncertainties. The preprint, Archive 2509016664, was submitted in early September. The published version appeared in February 2026. The community read it carefully. The Bullet team noted that Capitaro's question was about to be tested by the same kind of multi-epoch imaging they had already scheduled. The waiting room of astronomy in early 2026 was a peculiar place. Several deeply consequential results were all quietly approaching completion on roughly the same schedule. Winter arrived. The Bullet team prepared their analysis pipeline for the second epoch. They wrote the astrometric registration scripts. They calibrated the expected systematic errors. They modeled the precision they would achieve, given the brightness of both targets, the angular resolution of NIRCam, and the availability of stable reference stars across the field. They expected to be able to measure proper motion at a precision of roughly 3 to 10 milliarcseconds. If the objects were galaxies, the result would be 0. If they were nearby brown dwarfs, the result would be tens to hundreds of milliarcseconds per year. There would be no ambiguity. The second epoch NIRCam observations took place on January 21, 2026, one day after the calendar anniversary of the first epoch. The pointing was identical. The filters were the same. The integration times were matched as closely as possible. The data arrived back on Earth within a few days. The pipeline ran. The astrometric registration completed. The proper motion measurement was performed. Picture the moment. A small office somewhere at the University of Ljubljana, or at a workstation in California, late on a winter afternoon. The processed second epoch images are sitting in a window on a screen, beside the first epoch images from exactly 1 year before. A team member aligns both datasets on the same reference stars, bringing them into the same coordinate frame. The two faint red points that launched a year of careful waiting are visible in both images. Bullet BD1 has moved 49 milliarcseconds across the sky in 12 months. The position the cursor settles on is one that no galaxy at the edge of the observable universe can occupy after a single year of observation. Galaxies, even relatively nearby ones, do not move detectably. Galaxies at the far boundary of cosmic time, whose light has been traveling toward us for nearly the entire age of the universe, would have proper motions of effectively 0. The team member moves the cursor to Bullet BD2. It has also shifted 24 milliarcseconds, less than Bullet BD1, but still unmistakably different from 0. Both motions point in roughly the same direction, about 20 degrees east of north. The angular separation between the two objects has barely changed. They are moving together, keeping pace with each other across the sky. They might be a wide, co-moving binary pair, two brown dwarfs gravitationally bound to each other. Or they might be an unrelated coincidence of two independent objects at similar distances, moving in similar directions through the disk. That question remains open. But the larger question does not. These two objects are not at the edge of the universe. The thing that appeared to sit at the edge of cosmic time was inside the Milky Way galaxy the entire time, drifting slowly across the sky at sideways velocities of roughly 116 kilometers per second for the brighter object, a speed consistent with the kinematics of the Milky Way's thick disk. They had been here all along. They were hiding in plain sight inside one of the most carefully studied fields in modern astronomy, mimicking the most distant galaxies ever observed, because the spectral break they produced in broadband photometry happened to fall at precisely the same wavelengths as the Lyman break of objects at redshift 20 and redshift 30. The universe had spoken. 2 faint red points in the bullet cluster field were not at the edge of cosmic time. They were in our own galactic neighborhood, drifting through the disk. With the proper motion result in hand, the brown dwarf interpretation, which had been the slightly favored reading of the near-spec spectra for the past 10 months, now had no remaining competition. There was nothing else this could be. The thing at the edge of the universe was a teacup temperature failed star. To understand what the team found when they went back to re-examine the near-spec prism spectra of bullet BD1 and bullet BD2 with the proper motion result confirmed, we need to spend a little time with a coincidence in physics. It is the coincidence at the heart of the entire story, the reason the dropout method, which has been right thousands of times over 30 years, was wrong for these 2 particular objects. 2 completely unrelated kinds of objects, separated not by a few thousand light years, but by the better part of the entire observable universe, leave essentially the same fingerprint in low-resolution broadband photometry. In the case of a high redshift galaxy, the fingerprint is the Lyman break. We described this earlier. Neutral hydrogen spread through the vast spaces between us and the galaxy absorbs all photons below the redshifted Lyman limit, about 912 angstroms in the galaxy's own rest frame. The result is a sharp cliff in the spectrum, a wavelength below which the galaxy is essentially dark, and above which it glows roughly as expected. For a galaxy at redshift 20, that cliff falls near 1.9 microns. For a galaxy at redshift 30, it falls near 2.8 microns. James Webb broadband photometry detects the galaxy in filters above the cliff and finds nothing in filters below it. In the case of a cool brown dwarf, the fingerprint comes from something entirely different. A brown dwarf is a small, dense object that sits in the gap between the most massive planets and the least massive stars. The coolest known brown dwarfs, those in the Y class, have surface temperatures ranging from about 250 to 500 Kelvin. At those temperatures, the atmosphere is dominated by molecules rather than atoms. Methane, water vapor, ammonia, hydrogen sulfide, and carbon dioxide are all present in significant amounts. Each of these molecules absorbs light at specific infrared wavelengths. Methane has particularly strong absorption near about 3.3 microns, and again near 8 microns. Water has strong absorption near 1.4, 1.9, 2.7, and longer microns. The combined effect of all these molecular absorbers is to carve the brown dwarf spectrum into a distinctive shape, regions of relatively higher emission separated by deep absorption troughs. For a Y-class brown dwarf at around 300 to 400 Kelvin, the combined water and methane absorption below roughly 3 to 4 microns strongly suppresses the object's near-infrared brightness. The same brown dwarf then emits considerably more brightly at somewhat longer wavelengths, between about 4 and 5 microns, where the molecular absorbers happen to leave a relative gap. The result is a spectrum that rises sharply from the suppressed shorter wavelengths toward the brighter longer wavelengths. And in the standard broadband photometry tools astronomers use to identify galaxy candidates, that rise looks almost identical to the Lyman break of a high redshift galaxy. Same wavelength range, same general shape. In low-resolution data, the two are essentially indistinguishable. When the Bullet team fit their near-spec prism spectra with a range of candidate models, the brown dwarf templates performed slightly better than the high-resolution galaxy templates. The fits used a software pipeline called UCD-MCMC, applied to the ELF-WLY 2025 model grid developed by Adam Bergesser and collaborators.
For bullet BD1, the best fit effective temperature was 350 Kelvin, with an uncertainty of about plus 110 and minus 80 Kelvin. The chi-squared per degree of freedom was 1.3. For bullet BD2, the best fit temperature was 410 Kelvin, with an uncertainty of plus 110 and minus 50 Kelvin, and a chi-squared per degree of freedom of 0.9. The Galaxy template fits gave chi-squared values of 1.4 for bullet BD1 and 1.2 for bullet BD2. The brown dwarf fits were better, but only modestly. On chi-squared grounds alone, the team could not have committed. They needed the proper motion test. Now that they had it, the spectroscopic fits became confirmatory rather than decisive.
To translate those temperatures into something more tangible, 350 Kelvin is about 77 degrees Celsius, or around 171 degrees Fahrenheit. That is the temperature of a cup of tea that has been sitting on a counter for a few minutes, still warm enough to notice, still slightly unpleasant if spilled on your hand, but a long way from boiling. 410 Kelvin is closer to 137 degrees Celsius, or about 278 Fahrenheit. That is somewhere in the territory of a low oven setting, above the boiling point of water, but not quite hot enough to bake bread. These were the surface temperatures of the brown dwarfs that the world's most capable infrared telescope had been attempting to interpret as galaxies at the dawn of cosmic time. The most distant thing in the picture was the temperature of a teacup. There is something worth sitting with in that fact. Two completely unrelated physical processes, operating in two completely unrelated kinds of objects, in two completely unrelated corners of the universe, leave the same fingerprint in our best data. Hydrogen absorbing the light of a galaxy that formed 90 million years after the Big Bang. Methane and water absorbing the light of a failed star drifting through the disk of the Milky Way about 1,600 light-years from Earth. These processes share no physical mechanism. The hydrogen absorption is an atomic process working across cosmological distances on light that has been traveling for 13.5 billion years. The methane and water absorption is a molecular process working in a stellar atmosphere on light that has been traveling for 1,600 years. The two have nothing in common, except that both produce a sharp transition in the spectrum at overlapping wavelengths. By an accident of physics that nobody designed, nobody chose, and nobody anticipated, the Lyman break of the highest redshift galaxies and the molecular absorption edge of the coldest brown dwarfs happen to fall in the same part of the infrared sky. They are accidental homonyms in the language the universe speaks to us through light. This is the moment where something quietly shifts in the story. The two faint red points in the bullet field, which the team had been treating as a puzzle to solve, become something closer to a question to sit with. The universe is communicating in a language that contains accidental homonyms, and our best instruments, at this particular level of precision, cannot fully distinguish between them. The implication is heavier than it sounds. It means that some fraction of the most extreme high redshift galaxy candidates ever cataloged in any deep field with any instrument may not be galaxies. They may be cold, local brown dwarfs that happen to share the spectral fingerprint. The Braidach team's result was not an isolated accident. It was a particular expression of a more general property of the universe and of the boundary of what our current measurements can resolve. The bullet team carried that thought into the final stages of the analysis. They wrote the paper. They posted it to archive as preprint 2604-23668 on April 26, 2026. The title was direct. Two exciting high redshift galaxy candidates turn out to be two exciting ultra-cool brown dwarfs. The implication was clear. They were casting a careful and honest shadow not only over their own result, but over Capitoro, and more broadly over a fraction of the extreme high redshift literature. The community's response was largely to accept the result and to accelerate proper motion follow-up campaigns on every other extreme high redshift candidate that could plausibly be a contaminant. The cleanup is still underway in 2026. To really understand what was sitting in the bullet cluster field, what the team had been pursuing for a year, and what turned out to have been hiding so quietly in plain sight, we need to spend some time with the object itself. We need to understand what a Y-class brown dwarf actually is, because the answer is one of the stranger entries in modern astronomy's catalog, and there's a good chance you've never had a clear picture of one in your mind.
A brown dwarf is, in the most direct sense, a failed star. Stars form through the gravitational collapse of cold clouds of interstellar gas, mostly hydrogen with some helium and traces of heavier elements. As a cloud contracts, gravitational potential energy converts to heat. The temperature at the center climbs. If the collapsing mass is large enough, somewhere around 75 to 80 Jupiter masses, the core temperature and pressure eventually reach the threshold required for sustained hydrogen fusion to ignite. The new star settles onto the main sequence, where it will spend millions to billions of years quietly converting hydrogen to helium and shining with steady light. The Sun is one of these. Every star you can see in the night sky is one of these.
A brown dwarf is what forms when the collapse stops just short of that threshold. The cloud is not quite massive enough. The central temperature never quite reaches the value required for sustained hydrogen fusion. The object that results still carries an enormous reservoir of heat from the energy of gravitational collapse, but it has no nuclear furnace to replenish what it radiates. So the brown dwarf cools. It radiates its accumulated heat gradually into the space around it, growing dimmer over millions and then billions of years, slowly drifting toward thermal equilibrium with the interstellar medium. The boundary between brown dwarfs and the lowest mass stars sits at about 75 Jupiter masses. The boundary between brown dwarfs and the most massive planets sits near 13 Jupiter masses, the threshold at which brief deuterium fusion occurs during the object's early life. Objects above 13 Jupiter masses fused deuterium briefly in their youth and are called brown dwarfs. Objects below it never did and are called planets. The distinction is somewhat philosophical, and there is an active ongoing debate about whether formation pathway should matter more than mass, since some objects form by collapsing from an interstellar cloud, while others accumulate in protoplanetary disks around forming stars. The deepest James Webb surveys are beginning to find free-floating planetary mass objects in young star clusters, like the trapezium cluster in Orion, where a 2023 survey by Pearson and McCowarin reported more than 500 such candidates, many of them in apparent binary pairs. The classification scheme for brown dwarfs follows their decreasing temperature with a letter sequence, M, L, T, Y. The M dwarfs are the coolest true stars, with surface temperatures from roughly 2500 to 3700 Kelvin. The L dwarfs, introduced by David Kirkpatrick and collaborators in the late 1990s in a paper in the Astrophysical Journal, volume 519, page 802, span temperatures from about 1300 to 2400 Kelvin, populated mostly by very low-mass stars near the hydrogen burning limit, and by younger, hotter brown dwarfs that have not yet cooled below their formation temperatures. The T dwarfs, characterized by the strong presence of methane absorption in the near-infrared, were first systematically defined by a team led by Adam Burgosser in 2002. T dwarfs occupy the temperature range from roughly 500 to 1300 Kelvin, and their atmospheres are dominated by methane in much the same way that Jupiter's atmosphere is.
The Y class is the coolest known category, with effective surface temperatures below about 500 Kelvin. It was formally defined by Michael Cushing and collaborators in 2011, based on cool objects discovered by NASA's Wide Field Infrared Survey Explorer, WISE. The defining spectral signature of the Y class is ammonia absorption in the near-infrared, which becomes prominent below about 500 Kelvin and is absent in T dwarfs. Y dwarfs are divided into subclasses from Y0 through Y2 and beyond, with progressively lower temperatures.
The coldest known brown dwarf is WISE J0855-0714, often called simply W0855, discovered by Kevin Luhmann in 2014 and characterized in subsequent papers through 2024. Its effective temperature is approximately 250 Kelvin, around -23 degrees Celsius or -9 degrees Fahrenheit. It is cooler than the freezing point of water. It is the temperature of a chest freezer. It is the lowest known surface temperature of any free-floating object beyond the solar system, and it sits only about 7 light-years from Earth in the constellation Hydra, making it one of the closest known objects beyond our own planets and sun.
The cooling timescales for brown dwarfs are long. A brown dwarf of about 30 Jupiter masses takes roughly 5 billion years to cool below 500 Kelvin, and approximately 10 billion years to reach 300 Kelvin. The universe is about 13.75 billion years old. A brown dwarf at 300 Kelvin today has therefore been cooling steadily for some 10 billion years, since a time when our sun did not yet exist and the Earth had not yet assembled from the debris disk around a forming yellow star. The cool brown dwarfs drifting through our galactic neighborhood are, in a genuine and meaningful sense, fossils of an early era of Milky Way star formation. Each one is a small, dim record of conditions in our galaxy's distant past. Now picture the surface of bullet BD1. If it had a clearly defined surface in the way a rocky planet does, it doesn't quite, but suppose you could find yourself at the boundary between the atmosphere and the deeper interior. The sky above you would be dense and gray-brown. The dominant molecules would be methane and water vapor, with smaller amounts of ammonia, hydrogen sulfide, and carbon dioxide. The methane would give the atmosphere a faint brownish tint at certain depths. At the cooler upper layers, water vapor would condense into ice crystal clouds, in the same way moisture condenses into clouds on Earth, but at temperatures and pressures very different from anything in our familiar atmosphere. Higher still, thin wisps of ammonia ice would drift through atmospheric convection currents, the ammonia condensing at the coldest tops of the cloud layer. Above you would be no sky in any familiar sense. Bullet BD1 is alone in interstellar space, with no host star to orbit, no external light to illuminate its clouds, no warmth arriving from outside. The only light would be the dim infrared glow of the object itself, the residual warmth of billions of years of slow cooling, radiating gradually outward into the cold dark surrounding it. The temperature at what passes for the surface would be about 350 Kelvin, roughly 77 degrees Celsius. Warm enough to be unpleasant if it touched your skin, not hot enough to burn. Something like being inside a warm, dark, airless room with no windows and no sky. The gravity would be several times what you experience on Earth, pressing you firmly against whatever structure exists below. Convection cells would be circulating the interior's heat upward and drawing cooler material down, a slow, perpetual churning, carrying warmth from the interior toward the surface. There would be no horizon, no sun, no civilizations, and no prospect of any. This object has been cooling alone, drifting through interstellar space for something on the order of 10 billion years. It is older than the Earth. It is older than the Sun. It will continue cooling for billions of years more into the deep future of the universe, long after the Sun has exhausted its hydrogen and expanded into a red giant, long after the Earth has been consumed, long after our solar system has become something barely recognizable. Bullet BD1 will still be here, drifting and cooling, losing its heat one quiet photon at a time. This is what was sitting in the bullet cluster field. Not a galaxy at the dawn of cosmic time, not a luminous structure assembled from billions of early stars in the universe's first 100 million years. Something far stranger and much closer. A failed star, drifting alone through the disk of our own galaxy 1,600 light-years from Earth, slowly settling toward the cold of the cosmic background, casting its dim infrared light across space toward the James Webb's waiting mirrors. The same object that, by an accident of physics, carries a spectral signature resembling the red-shifted Lyman break of the most distant galaxies imaginable. From the outside, in our broadband photometry, the two look nearly identical. From the inside, they have nothing whatsoever in common. The Broddock team's bullet cluster result was striking because it identified two specific brown dwarfs in a specific field. But the deeper question raised by the result was about the population as a whole. How many of these objects are actually out there in our galaxy, hiding in the deepest James Webb images, wearing the disguise of a galaxy at the edge of cosmic time? The answer has been taking shape through a parallel research program conducted mostly through the JWST survey, the JWST Advanced Deep Extragalactic Survey, led by a team including Kevin Hanine at the University of Arizona. JWST is one of the most ambitious deep field programs ever attempted, covering the Goods South and Goods North fields to depths that no previous extragalactic survey has approached. Its primary goal is to characterize the population of galaxies in the first billion years of cosmic time. An important secondary outcome has been the identification of a substantial brown dwarf population hiding in the same fields. In their 2026 analysis paper, Archive 251-00011, titled JWST, An Abundance of Ultra-Distant T and Y Dwarfs in Deep Extragalactic Data, Hainline and collaborators reported the identification of 41 brown dwarf candidates across the two Goods fields. Of these, 31 were classified as T dwarfs and 10 as Y dwarfs. The T dwarfs appeared at distances ranging from a few hundred parsecs out to about 5 or 6 kiloparsecs, spanning a substantial fraction of the width of the Milky Way disk. The Y dwarfs, being cooler and therefore fainter, were necessarily found closer, at distances from about 100 parsecs out to roughly 2 kiloparsecs. The team introduced a Bayesian fitting tool called NIFTY for systematically distinguishing brown dwarf spectral energy distributions from those of galaxies. When these surface densities are extrapolated across the full sky, the numbers are substantial. The Y dwarf surface density in the JWST depth fields is approximately 0.02 per square arcminute. The T dwarf surface density is approximately 0.1 per square arcminute. There are about 150,000 square arcminutes in the entire sky. Scaling from these figures suggests something on the order of 3,000 Y dwarfs and 15,000 T dwarfs detectable at JWST depth magnitudes across the whole sky. The total population of Y dwarfs in the Milky Way, including the vast majority that are too faint for current instruments, is almost certainly in the tens of millions, or perhaps the hundreds of millions. The total brown dwarf population across all subclasses, from late L through Y, is likely comparable to or larger than the population of low-mass main sequence stars. This is a quietly remarkable thing to sit with. The Milky Way is in part a galaxy of failed stars. The objects we have been cataloging and counting for centuries as stars are only the brightly visible portion of a much larger population, much of which has been cooling in the dark for billions of years, scattered through the disk, too faint for any pre-JWST telescope to detect in any systematic way. Brown dwarfs are not a small curiosity at the bottom of the stellar mass function. They may be the most common kind of stellar mass object in the galaxy. The familiar textbook picture of a Milky Way containing 100 to 400 billion stars may need to be quietly updated to acknowledge a comparable population of objects that did not quite reach stellar status, but exist in similar or greater numbers. What does this mean for our story? It means Bullet BD1 and Bullet BD2 were not isolated discoveries. They were not a lucky accident in one particular field. They were a property of our galaxy revealed for the first time by the depth, sensitivity, and multi-epoch imaging capability of the James Webb. They are typical, not exceptional. There are almost certainly thousands more like them sitting in James Webb deep field catalogs right now, waiting to be identified through careful follow-up work. The Hainline Group's NIFTY tool and the Brodach team's combined spectroscopy plus proper motion approach are beginning to allow systematic cleanup of the high redshift catalogs. Current estimates put the contamination rate in deep fields at approximately 0.1%, which sounds small until you consider that JDOS alone has produced tens of thousands of candidates. Even one contaminant in 1,000 means dozens of misidentified objects across the deepest extragalactic surveys. The bullet cluster brown dwarfs are the most visible instance of this so far. They are not the last. What we have just witnessed, looked at carefully and honestly, is the dropout method being audited in real time. The method works. It has worked for 30 years. It identified thousands of high redshift galaxies through the Hubble Deep Field, the Hubble Ultra Deep Field, CANDLES, GOODS, JADES, SEERS, and more than a dozen other programs. The Lyman break technique is not broken. What we have learned is that the method, like every powerful technique in science, has an edge case,
And in this particular instance, the edge case is the population of cold local brown dwarfs, whose spectral signatures happen to overlap the Lyman break signatures of objects at the very dawn of cosmic time.
Stadl's original 1996 paper, the founding document of the technique, did not anticipate this failure mode. It did not need to. The galaxies he was searching for were at redshift around 3, where the Lyman break falls in the near ultraviolet, far from any wavelength region where a brown dwarf would be a significant contaminant. The brown dwarf classification system had not yet fully been developed. The L class was introduced in 1999, the T class in 2002, the Y class in 2011. Systematic study of brown dwarf atmospheric spectra at the temperatures relevant to the contamination problem only became possible with WISE in 2009 and 2010, and with the James Webb starting in 2022. The problem could not have been seriously studied before the relevant data existed.
As the dropout method was extended to higher and higher redshifts over the decades, the predicted location of the spectral break shifted progressively into the infrared. By the time the James Webb began searching for galaxies at redshifts of 10, 15, 20, and beyond, the predicted break fell squarely in the wavelength range where cool brown dwarf methane and water absorption produces a similar-looking transition. The collision of these two signatures was, in retrospect, inevitable.
The first papers documenting the contamination began appearing in 2023. Langarotti and Heiwert published their identification of 3 brown dwarfs masquerading as highly reddened AGN candidates, archive 23081090, that year. Hainline and collaborators published their foundational brown dwarf candidate paper for JDs and CEs in 2024. Bergasser's Rubies program in 2024 announced 7 cold and distant brown dwarfs identified as contaminants. The Hainline 2025 paper published 3 brown dwarfs masquerading as high-reddened AGN galaxies in JWST observations, archive 2501166448, examined the systematic prevalence of the contamination more closely.
That team analyzed 14 high-redshift galaxy candidates from JADES and CEERs that had received near-spec follow-up spectroscopy. 3 of the 14 turned out to be brown dwarfs. The estimated contamination rate was approximately 0.1% of deep-field high-redshift candidates overall, with the rate rising significantly for the most extreme candidates and for fields at low galactic latitudes where the brown dwarf population is denser.
What these systematic studies have revealed is that the dropout method applied to the deepest James Webb extragalactic surveys is producing 2 kinds of answers from the same fingerprint. One answer is the genuine high redshift galaxies that the technique has been correctly identifying for 3 decades. The other is the cold brown dwarf contaminants that the technique has been silently misidentifying because the underlying spectral physics happens to produce indistinguishable signatures in low-resolution broadband photometry. 2 answers from the same fingerprint. It is a useful way to hold the problem in mind, not a flaw in the method, a property of the universe. 2 kinds of objects exist that, at this level of detail, look the same. The task of the method, and of the astronomers using it, is to layer in the additional cross-checks that distinguish the 2.
The cross-checks that have proven most useful are proper motion measurement, high-resolution spectroscopy, and combined photometric fits that explicitly include brown dwarf templates alongside galaxy templates. Proper motion is the most decisive of the 3 because it is fundamentally an astrometric measurement rather than a spectroscopic one, and the 2 physical situations make completely different predictions. A galaxy at redshift 20 must have 0 detectable proper motion. A brown dwarf at 500 parsecs will have tens of milliarcseconds of drift per year. Once the measurement is made, there is no remaining ambiguity.
High-resolution spectroscopy, when it is available, is equally decisive, revealing the molecular absorption features of the brown dwarf atmosphere, the methane, water, and ammonia bands that are simply absent from the spectrum of a high redrift galaxy, which would instead show an ultraviolet stellar continuum and possibly emission lines from young, massive stars forming within it. At the level of low-resolution broadband photometry, the differences average out into the same-looking spectral break. At higher spectral resolution, the 2 have nothing in common.
The community has been incorporating these cross-checks systematically,
Every new extreme high redshift candidate worth confirming is now receiving near-spec follow-up at higher resolution where feasible. Multi-epoch imaging programs are being scheduled to enable proper motion measurement for the most uncertain cases. Bayesian fitting tools that explicitly compare brown dwarf and galaxy templates, like the Nifty tool from Heinlein's group and the related UCD-MCMC framework from Bergasser, are being adopted as standard parts of the analysis workflow.
The dropout method itself has not changed. The scaffolding of verification around it has, and the high redshift catalogs of 2025 and 2026 are being gradually cleaned, with a small but real fraction of previously claimed early galaxies being quietly reclassified as nearby brown dwarfs. There is something quietly admirable in this process. The community has not suppressed the problem. It has not buried the inconvenient reclassifications. It has instead published them openly, including the most striking cases, even when those cases involve stepping back from previously announced records. The Bratatoch team's paper, its title an honest admission that two exciting galaxy candidates turned out to be two exciting brown dwarfs, is exactly that kind of correction. The galaxy candidates were genuinely exciting. They turned out to be brown dwarfs. The brown dwarfs are also genuinely exciting, perhaps more so in some ways, because they reveal a population of ancient failed stars in our own galactic neighborhood that no previous telescope could have systematically detected. The story has not become smaller because the galaxies turned out to not be galaxies. It has become differently large.
We need to return to Kappa-Taro now, because the bullet cluster story is not quite complete without it. Kappa-Taro is the case where the same fundamental question remains unresolved. It is the case where the proper motion test that definitively settled bullet BD1 and BD2 has not yet been completed. It is where the community is still waiting for the measurement that will decide between the brown dwarf interpretation and the alternatives that remain live. Recall that Kappa-Taro is the nickname for CERRS U10058, the F356W dropout found by Gandolfi and her collaborators in the CERRS deep field in the constellation Bootes at coordinates right ascension 14 hours, 19 minutes, 32.97 seconds, declination plus 52 degrees, 47 minutes, 52.11 inches. The photometric redshift, if this object were a galaxy, gives a value of approximately 32, placing the universe at roughly 90 million years old at the time the light was emitted. That is 200 million years earlier than the current spectroscopically confirmed record. It falls squarely in the era when, according to standard galaxy formation models, even the most efficient early star formation would not have had time to assemble anything bright enough to be detected.
By 2026, 3 competing interpretations of Kappa-Taro have crystallized in the literature. Each has papers behind it. Each has researchers actively considering it. The interpretations are not exactly opposed. They are in suspension, waiting for the measurement that will resolve which one is correct. The first interpretation is that Kappa-Taro is precisely what the dropout method suggests, a galaxy at redshift 32, the most distant galaxy ever observed, formed somehow in the first 90 million years of cosmic time. The advocates for this interpretation note that the photometric fit, while extreme, is not physically impossible, and that lensing magnification from a foreground galaxy could account for some of the apparent brightness. A 2025 paper by Young, Somerville, and Changa argued that the standard cosmological model is not actually broken at redshifts between 12 and 30, even given current observations, and that the apparent brightness of early galaxies can be accommodated within model uncertainties if one is careful. The galaxy interpretation remains alive.
The second interpretation is the one that gained ground following the bullet BD result. Kappa-Taro is an ultra-cool Y-class brown dwarf in our own galactic neighborhood, hiding in the CERS field, mimicking the most distant galaxy ever observed because of the methane and water absorption in its atmosphere. The Gandolfi 2026 ANA paper presented careful fits using the Sonora Chihuahua and ATMO 2020 model grids, suggesting a Y2 or Y3 brown dwarf at a surface temperature between 300 and 400 Kelvin, at a distance somewhere between 127 and 1800 parsecs.
The Heinlein 2026 paper independently confirmed the photometric fit, describing Capitaro as very likely an ultra-cool wide dwarf.
The third interpretation is the most exotic. Andrea Ferrara and collaborators in 2026, and a separate group led by Mangan and John, proposed that Capitaro could be a pair instability supernova, the final explosive death of a very massive primordial star. A star of roughly 140 to 260 solar masses would end its life through a process in which electron-positron pair production in the hot core destabilizes the star's internal pressure support, triggering a runaway thermonuclear reaction that detonates the entire star, leaving absolutely nothing behind. The light curve of such an event has a characteristic slowly declining shape, which cosmological time dilation would stretch from weeks to years if the event occurred at high redshift. If Capitaro were a pair instability supernova at around redshift 15, the spectral peak would fall in the F444W filter in the way the observations actually show. No such event has ever been directly confirmed. If Capitaro turned out to be one, it would be the first.
These three interpretations cannot all be correct. The data will pick one. The decisive test for Capitaro, exactly as it was for bullet BD1 and bullet BD2, is proper motion. A galaxy must have none. A brown dwarf at 100 parsecs will drift by 100 or more milliarc seconds per year. A brown dwarf at 1,000 parsecs will drift by 5 to 10 milliarc seconds per year. A pair instability supernova at redshift 15 will show no motion, but will additionally show a fading or evolving brightness over a multi-year baseline. The current proper motion upper limit from the existing 2.3-year CEER's imaging baseline is approximately 0.137 arcseconds per year, not yet precise enough to distinguish between a distant brown dwarf and a stationary extragalactic source.
A new multi-epoch James Webb campaign is needed to push the precision down to the level of a few milliarc seconds per year. That campaign is in the JWST observing queue for 2026. The data is expected to begin arriving by late summer or early autumn of 2026.
Imagine, if you will, the night when the second epic image of Capitaro is finally collected. The James Webb is drifting at L2, 1.5 million kilometers from Earth, in its slow orbit around the second Sun-Earth Lagrange point. The mirrors have been pointed at Boötes, at the small patch of sky that contains CERR's U10058. The integration is running. Photons are arriving at the detector, perhaps just a handful per second, from the faint red point that is Capitaro. The data will be transmitted to Earth within a few days. The pipeline will run. The astrometric registration will be completed. The comparison will be made.
The single pixel containing Capitaro will either be in the same place it was 3 years ago, or it will have drifted slightly to one side. If it has not moved, we are looking at one of the most extraordinary objects in the history of cosmology. Either a galaxy at the dawn of time, more remote than any object ever spectroscopically confirmed, or a pair instability supernova that brought a primordial star's death directly to our detectors. Either alternative would be a genuine discovery. Either would change something.
If it has moved, we are looking at a 1 in 1,000 coincidence that has held the attention of the cosmological community for 2 years. A Y-class brown dwarf, so cold, so dim, so red, so far from the galactic plane, that it survived the first pass of deep field filtering and ended up in the catalog of high-resolution galaxy candidates. The mythology around Capitaro would gently deflate. The community would absorb the result, update the catalogs, and continue. The current photometric evidence favors the brown dwarf interpretation. Both the Heinlein 2026 paper and the Gandolfi 2026 A&A paper came to similar conclusions on photometric grounds. But photometry is not enough. The community has learned through the bullet BD experience that chi-squared comparisons of photometric templates are not decisive, and that proper motion is the test that actually resolves the question. So we wait. The data is in the pipeline. The most distant thing in the picture might also be the closest. That phrase, which began as a metaphor, has become the active question.
For now, in the spring and summer of 2026, Capitaro remains the unfinished corner of this story.
If we step back from the technical details and the specific objects and the individual fields, the deeper lesson of this story is about boundaries. It is about how clean a distinction we thought we had drawn between the local universe and the distant universe, between the galactic neighborhood that contains the sun and the cosmic dawn of the first galaxies. The lesson is that this distinction is fuzzier than the textbooks have always implied, and that fuzziness is not a measurement error. It is a property of the universe itself. The cosmic distance ladder is the conceptual scaffolding by which astronomers infer how far away things are. The lower rungs are well calibrated and reliable. Trigonometric parallax, the apparent shift of a nearby star against background stars as the Earth moves around the Sun, gives direct distances out to a few thousand parsecs. Standard candles like Cepheid variables and Type A supernovae extend the ladder out to hundreds of megaparsecs. The recession velocities of distant galaxies combined with Hubble's law give us distances at cosmological scales. Each rung is calibrated against the one below it. The whole system has been refined over a century, and the distances to most galaxies in the sky are now known to within about 10 to 20%.
What the bullet cluster brown dwarf story reveals is that one of the ladder's foundational assumptions, that we can clearly distinguish foreground objects from background ones, has a specific edge case. The assumption holds almost always. Most stars in any deep image are clearly recognizable as nearby stars. Most galaxies are clearly background galaxies. The two populations have different colors, different spatial distributions, and different responses to multi-wavelength photometry. The rare cases where the distinction blurs are usually apparent in retrospect once additional data is available.
Ye-class brown dwarfs at the edge of the high redshift catalogs are not apparent. They were not identified in the first decade of James Webb operations. They required follow-up spectroscopy and multi-epoch imaging to be separated from the most distant galaxy candidates the telescope was built to find. They sit in the same fields as genuine high redshift galaxies. They produce nearly identical broadband fingerprints. They differ only in measurements that require time, patience, and effort to obtain.
The cosmic distance ladder in this corner of the sky has been quietly contaminated by an unrelated population that was only discovered to exist in significant numbers after the surveys were already underway. The JWST broke cosmology headlines of 2023 and 2024 were always in part a misreading. The early extreme high redshift candidates that drove the most dramatic headlines were a mixture of genuine breakthrough discoveries and unrecognized brown dwarf contaminants. The cleanup that has been underway since 2025 has been quietly reducing the apparent tension between observations and the standard cosmological model.
Some of the candidates that generated the most striking claims have been reclassified. The remaining genuine high redshift galaxies, including JD's GS-Z14-0 and MOM-Z14-M, are real, spectroscopically confirmed, and still surprising in their brightness and abundance, which remains one of the legitimate open questions in galaxy formation today. But the apparent redshift 30 and redshift 32 candidates that fueled the most extreme version of the cosmology is broken narrative have in some cases turned out to be local brown dwarfs. The Lambda CDM model is doing better than it appeared to be doing 2 years ago.
This is the recalibration. The universe is still strange, but the strangeness has been redistributed. Some of what we attributed to the very early universe has turned out instead to live instead in our own galactic neighborhood. The Milky Way contains failed stars old enough to approach the age of the universe itself, cool enough to mimic galaxies at the dawn of time, and abundant enough to contaminate the deepest catalogs ever assembled. Sit with this for a moment. The picture you have probably been carrying around, perhaps without ever putting it into words, goes something like this. The Milky Way is our local home, a galaxy containing the sun and the stars you can see on a clear night, surrounded by vast cosmic emptiness. Beyond it lie the other galaxies, the galaxy groups and clusters, the cosmic web of large-scale structure, and the deep spaces between its strands.
At the very furthest reaches, at the edge of the observable universe, sit the first galaxies ever formed, only a few 100 million years after the Big Bang, visible to us as faint red points in the deepest infrared surveys. The picture is clean. The local universe is here. The distant universe is there. No overlap.
What the bullet cluster brown dwarf result and the broader James Webb contamination work has been telling us for 2 years is that the picture is wrong in one specific and important way. The boundary between the Milky Way and the distant universe in our deepest images is not a sharp wall. It is a fog. And the fog is made of failed stars, drifting slowly through our own galaxy, having been there all along, waiting to be noticed. The map of cosmic distance has a fuzzy region at its furthest reaches, a population of foreground objects that mimic background objects. The only way to see through the fog is to do the careful, patient, multi-year work of spectroscopy and astronomy that the Bradachak team did in the bullet field. The intellectual honesty of admitting this matters. The community could have been quiet about the contamination problem. It could have buried the reclassifications of previously announced high redshift candidates. It did not. It published openly. It walked back the records that needed walking back. It celebrated the brown dwarf identifications as their own kind of remarkable result. The system of correction works. The headlines of 2024 were partially premature. The slower, more careful work of 2025 and 2026 has reshaped the field. What you might feel listening to this is something like a soft equilibrium. The universe is not broken. The cosmological model is not broken. The dropout method is not broken. What has happened is that an edge case of the method has been carefully documented. The cross-checks needed to resolve it have been developed, and the catalogs are being cleaned up. The strangeness has been redistributed from a place we cannot reach to a place 100 parsecs from the sun. The strangeness is closer than we thought. It has been closer the whole time. We had simply not yet looked carefully enough to see it. Sit with this for a moment, in the way that someone listening late at night can really sit with a thought. 350 Kelvin, slightly warmer than a cup of tea left cooling on a window ledge. The most distant object the world's most powerful infrared telescope had ever extracted from the bullet cluster field turns out, on careful inspection, to be the temperature of something you could hold in your hands without discomfort. The most extreme galaxy candidate in one of the most carefully studied images of the early universe is cooler than the inside of your car on a summer afternoon, cooler than your oven on its lowest setting, barely above the temperature at which water boils. The distance to this object is approximately 1,600 light-years, or about 500 parsecs. That is the distance to the Pleiades, the small, bright cluster of stars visible to the naked eye in winter. The Seven Sisters, which have appeared in human mythology for at least 4,000 years. Bullet BD1 is closer than the Orion Nebula. It is far, far closer than the center of the Milky Way. In the grand scale of cosmic distances, it is our neighbor. The light it emits crosses 1,600 years of space to reach the James Webb's mirrors. By contrast, the light from a galaxy at redshift 14 has been traveling for 13 billion years, an interval 10 million times longer. The proportions are difficult to hold in your mind all at once. The age of the object is approximately 10 billion years. We can't pin that down precisely, but the temperature gives us a strong constraint. To have cooled to 350 Kelvin, a brown dwarf of about 30 Jupiter masses has needed to be radiating its heat steadily into space for somewhere around 10 billion years. The Sun is about 4.6 billion years old. The Earth is younger than the Sun. The first life on Earth appeared perhaps 3.5 billion years ago. Bullet BD1 was already settling toward its current temperature for billions of years before the rock under your feet had assembled itself from the disk of gas and dust around a newborn yellow star. It has been here, drifting through the disk of the Milky Way at thick disk speed, roughly 116 kilometers per second,
for as long as the universe has had a Milky Way. And it will continue cooling, alone in the cold dark, for billions of years beyond the present moment. Long after the sun has spent its hydrogen and become a white dwarf, long after the Earth has been consumed, long after our solar system has become something barely recognizable.
This is the object the world's most powerful telescope briefly mistook for the most distant galaxy ever observed. This is the failed star the dropout method had been quietly miscounting in deep fields. This is what the Brodach team caught with a year of patient measurement in the bullet cluster field. And the strange dignity of it is that the object is not less remarkable for not being a galaxy. If anything, it is more remarkable. It is a 10-billion-year-old fossil of early Milky Way star formation, cooling toward equilibrium with the interstellar medium, sitting in our own neighborhood, having been here the whole time.
The universe contains objects this strange. They share our galactic neighborhood. They have been doing so for billions of years, before any of us were born, before the sun was born, before the Earth was born. The lesson is not that the dropout method is broken. We have already discussed this. The lesson is not that the cosmological model is broken. The lesson is that the universe sometimes speaks in accidental homonyms, and the work of astronomy is to learn to hear the difference.
The possible physical origin of these objects begins with a long series of questions. What scale of location is right for these kinds of objects? What about their fundamental properties? To paint a larger perspective, we need to call in corollary evidence. What kind of data can be combined with broadband photometry? What insights can be gained from combining orbital dynamics? How do these objects organize themselves? What kind of community might we see?
What this should leave you with, as you settle into the quiet of wherever you are listening, is not a sense of loss. The early universe has not been taken away. The spectroscopically confirmed records, JWST-GZ-Z14.0 at redshift 14.32 and MO-Z14 at a comparable redshift, remain in place. The cosmic dawn is still being mapped. The first galaxies are still being found. The dropout method, with the cross-checks now in place, will continue to be the primary tool of high-redshift galaxy science for as long as infrared telescopes exist in space.
What has changed is that we now have a more honest picture of how the universe presents itself to us. The boundary between near and far is fuzzy. The fog at the extreme edge of the cosmic distance map is real. The fog is made of failed stars in our own galactic neighborhood. They have been there the whole time. They've been there longer than the sun. And the James Webb has begun to see them, in 2s and 3s in the deepest infrared images ever taken, for the first time.
The Milky Way is not a sparse landscape with a few 100 billion scattered stars. It is a crowded place. Stars and brown dwarfs and free-floating planetary mass objects and clouds of gas and dust and dark matter, all woven into a structure we are only beginning to map. The brown dwarf population, hidden from every telescope that came before the James Webb because these objects are simply too faint and too cool to detect with anything less sensitive, is likely comparable in number to the low-mass star population. The galaxy contains tens of millions or hundreds of millions of failed stars drifting slowly through the disk and halo, cooling steadily over billions of years, occasionally being noticed when one of them drifts into the field of an instrument patient and precise enough to detect it.
Bullet BD1 and Bullet BD2 are two of them. They are not the only two. They are probably not even among the most interesting two. They are simply the two that, in early 2026, the Brodach team caught in the act of appearing to be the very edge of the universe. If you go outside on a clear, dark night, away from city lights, somewhere where the sky still has depth, and you look up, you will see thousands of stars with your bare eye. You will see, if you know where to look, the faint band of the Milky Way arching overhead. You will see, if your sky is dark enough and your eyes patient enough,
the faintest smudges of distant galaxies. What you will not see, with any telescope you can purchase, with any unaided observation, are the thousands or millions of failed stars cooling silently in the darkness of our galactic neighborhood. The James Webb sees them, a few at a time, in the deepest infrared images ever taken. Most of them are too faint even for the James Webb. The galaxy is full of quiet things that we have been overlooking for as long as we have been astronomers.
The bullet cluster brown dwarfs are a small, soft reminder of that. The cosmic web above your roof contains, at any given moment, a vast number of cold and dim objects that the most powerful telescopes ever built can barely detect. Some of those objects are, right now, masquerading as the most distant galaxies ever found, sitting in catalogs assembled by the most careful research teams in the field. Some of them will be identified in the coming years through the same combination of spectroscopy and multi-epoch imaging that resolved the bullet field. Some will continue drifting quietly through our deep field images, undetected, uncatalogued, contributing their photons to images nominally about the early universe, while actually being quiet, local things mixed in among the distant ones.
The map of cosmic distance has a permanent residual uncertainty at its furthest reaches that we will only ever be able to reduce, never fully eliminate. The closest things and the farthest things, in some small but real and permanent way, will continue to look the same, because the underlying physics of methane absorption and hydrogen blanketing happens to leave overlapping fingerprints, and no amount of methodological refinement will change that fundamental fact about how light interacts with matter at these particular wavelengths. The place that the bullet team kept returning to, half metaphor, half active working principle, was that the most distant thing in the picture might also be the closest. We have followed the arc of this story far enough now to know that the phrase is not metaphor. It is sometimes literally true. The faintest red point with the cleanest dropout signature in a James Webb broadband image can turn out to be a 500 parsec away brown dwarf drifting through the disk of our own galaxy, at the temperature of a slowly cooling cup of tea, older than the sun. The phrase, which began as a worried working hypothesis in a small office in Ljubljana or Davis in early 2025, has become something closer to a closing thought about what it means to look at the sky at all.
The cosmic web above your roof contains many quiet things. Some of them are very far away. Some of them are very close. From the outside, in low-resolution broadband photometry, they can be genuinely hard to tell apart. The work of astronomy is to tell them apart. The work goes on. The map of cosmic distance is being refined. The hidden population of failed stars in our galactic neighborhood is being mapped, one careful measurement at a time, in the deepest James Webb fields ever taken. The first galaxies are still being found. The cleanup is still underway. And on a clear, dark night, when you look up at the sky, the picture in your head should be a little softer at its edges than it used to be.
There is no hard wall between our galaxy and the early universe. There is a fog of failed stars drifting between us and the cosmic dawn, some of them only 1,600 light-years away, cooler than a cup of tea, older than the sun, drifting through the disk of the Milky Way at the unhurried pace of the thick disk population. They have been here the whole time. They will be here long after we are gone. They are not what we thought they were. In some quiet way, they are stranger and more wonderful than what we thought they were. They are not at the edge of the universe. They are in our backyard. And the most distant thing in the picture, by an accident of physics that nobody chose and nobody planned, might also be the closest. That is the lesson. That is what the bullet team found. That is what no one was quite ready for. The cosmos has been speaking in accidental homonyms, and we are only just beginning to hear the difference. Sleep well. The galaxy is full of quiet things. They are not going anywhere.